The topic of today's discussion is the center of gravity of composite bodies. As such, our objective are to discuss the location of the center of gravity and how we can actually calculate that, the location of center of mass, and the location of centroid using the method of composite bodies. There are some activities associated with today's discussion, including a reading quiz. We're going to discuss applications. I would take a look at some examples of how we can tackle some of these problems that involve method of composite bodies. You're going to take a look at a concept quiz. There is a group problem solving and attention quiz to wrap our session up. So before I start, let's take a look at these two rather short quizzes. Number one, a composite body in the section refers to the body made of blank. And there are four choices here, A, B, C, and D. The correct answer is actually, let's think about it for a minute. A composite body in this section refers to a body made of, well, carbon fibers and epoxy matrix. That is actually a composite fabric that are used. There are different types of composite we use for structural rehabilitation of older structures, bridges, what have you. It is not referred to steel and concrete. It is not referred to a collection of complex shaped parts or holes, but it is actually referred to a collection of simple shaped parts or holes. That's really the definition of a composite body in this section. Remember, when we use composites, they're also applied to aerospace industry and some cars nowadays. Most of the cars are made of composite material. So we are not talking about that. When we're talking about a composite in the context of statics and this course, we're talking about a collection of simple shaped parts or holes. Reading quiz number 2, the composite method for determining the location of the center of gravity of a composite body requires A, integration, B, differentiation, C, simple arithmetic, and D, all of the above. It really doesn't involve any of A, B, or D. All it takes is simple arithmetic, and you would see shortly some of the applications. So what are some of the applications of composite bodies and the way we actually need to calculate the center of gravity? An I-beam is a classical, typical example as such. It is used in a variety of shapes, and it used in a variety of applications in buildings, and the main reason for that is its efficiency of the shape and its moment of inertia and other reasons. So, and they're very smart components to design and work with geometrically, and they also save a lot of material in the process. And they're also T-sections, and they're also a typical type of a composite cross-section. As you can see, this is the cross-section of a T that I'm encircling in red. This cross-section is in T, and for the I-beam, it is that this cross-section that I am referring to. Later on, when you get into more advanced topics and design, you would see how these parts, these sections are used as an efficient part of the design of our structure. So when doing a stress or deflection analysis of the beam, it is very important to know the location of the centroids. Now, how can we calculate this? You would see in a minute. Other applications, let's say if you have a machine that's shown here, rests on supports A and B. This could be a compressor. The compressor, of course, consists of many individual components. These are the supports A and B that I just referred to. So we got a variety of components. We numbered them here. Component 1, component 2, component 3, component 4, component 5, and each of these components has its own center of gravity. So the question is, how can we determine the center of gravity of the entire assembly? Because it is very important in calculating the ground for the support structure. We definitely need to know the reactions at A and B. So if we know the center of gravity of each individual component, and then it would be nice to have methods and that we can use to calculate the center of gravity of the entire structure, the entire assembly. So how can we do that? How can we calculate the center of gravity or the center of mass of a composite body? That's the question that we try to address today. Consider a composite body. It consists of a series of bodies or particles. We name them here as the W1, W2, and in general we call it W sub n, from 1 to n. And for such a system, the net or the resultant weight would be given as W sub r, or simply the summation of all these W's from I1 to In. So it goes from 1 to n. Okay. So we're going to calculate the moments about the y-axis. In order for us to calculate the moment about the y-axis, we can actually calculate the moment of each individual body or a particle or component, whichever you want to call it, and then we can sum them up together. We can find a summation of that, and that would be the moment of the entire body about the y-axis. So what is x1 bar in this case, or x1 hat actually is a correct terminology, and x sub 2 hat and x sub n hat. Okay, those would represent the x coordinate of W sub 1, W sub 2, etc. So then we can sum the moments about the y-axis, and after doing so, we can do the same procedure for x and z-axis. So as you can see, x bar could be calculated as the summation of x hat w divided by the summation of w. And for y bar and z bar, we can do the same thing, except of course we have to change the coordinates because they have different coordinates with respect to y and z axis. So we can actually do that using these formulas and what we've learned from previous lectures. So if you replace w with m in these questions, we can find the coordinates of the center of mass. Remember, when we are dealing with center of gravity and center of mass, we need to calculate them. We need to come up with the coordinate. If it's in a 2D, then we need to look for the x coordinate and y coordinate. If it's in three-dimensional, then we need to look for x, y, and z components coordinate. That's the Cartesian coordinate system that we've been dealing with from the beginning of this course. So let's take a closer look at the concept of a composite body. There are two shapes here. One is on your left here, one is on your right. One of them is actually a typical cross-section of the barriers that you see in some of the roads during a temporary construction. They serve as temporary structures. They are very life-saving but simple devices. They're very good at absorbing the impact of a car if it hits them, and they've been tested and they've been used out there for many years. Of course, here the reinforcement of such a composite body is not shown, but it is designed in such an efficient way for many reasons. Now, why is it designed like that is really beyond the scope of our course here. That is for a reinforced concrete course. But if you look at the concept of a composite body, you can see that there are many composite bodies that do exist out there in the real world. What we try to do is we try to break them up into much smaller, simpler, more manageable sections, and then we would go ahead and do our calculations the way you would see shortly. So if we know the location of centroid or center of gravity for these objects, for these simple shaped parts, we can easily determine the location of the centroid or the center of gravity for the entire complex composite body that I just have shown you. So shortly you're going to see how we can actually do this. So there are some steps involved for the analysis. We would divide our structure into smaller, more manageable pieces. We call them shapes, we call them parts, we call them whatever you like. But we number them for the clarity and for the reasons of reducing the likelihood of errors. We would actually look at wholes as pieces. Of course, the mass of the whole or the portion in which it would contribute to the center of gravity must be subtracted from the other parts. You'd see that shortly, and it would become much more clear. Now we make a table with the first column for segment number, the second column for weight, mass, or size, the next set of columns for the moment arms, and finally we would have the columns for the intermediate calculations. And then we would fix the coordinate axis. We would determine the coordinates of the center of gravity of the centroid of each piece, and then we would fill in the table, and we would sum the columns to get the x bar, y bar, z bar, and we'd use the formulas that I just introduced you to those, and then we would actually find the location of the center of gravity, the centroid or center of gravity or center of mass. So the part shown here consists of 4 parts, A, B, C, and D. We would like to find the centroid of the composite, the entire composite object, and the plan is to follow those steps that I just mentioned shortly. So first, this body can be divided into 4 pieces. Remember that whole itself could be considered a piece. In that case, I need to subtract the area from the entire calculations to you'll be able to calculate the center of gravity of this particular, the centroid of this part. So we show that areas that need to be calculated with a negative sign. For steps 2 and 3, we would make up and fill in the tables using the parts that I just discussed. So let's take out the rectangle first. It has area of 6 times 3. Remember, if you continue the radius of the circle, you would see that this length would be 3. So the area of 6 times 8 is simply 18. 6 times 3, 18. The x hat is 3. It is assuming that the this point would be the origin of our calculations of our shape of our Cartesian coordinate system. Y hat is also would be half of that, of course, for A. The center of gravity of A, or centroid of A, should be somewhere here. I keep referring to the center of gravity as centroid, and I mean really centroid. So for the triangle, again, we take the area of the triangle. It is 3 times 1.5. and that is 4.5 square inch, assuming that all the units are given here in inches. That will be the area, and then the x hat would be 7. It is actually simply 6 plus 1, because for a triangle it's going to be 1/3 from here, 2/3 from the right hand side. Now these shapes and the locations of their centroid is given in your book in tables. You can refer to those tables to find what will be the centroid, the location of centroid of each of these individual components, such as a rectangle, triangle, circles, and so on. Then in this column, we simply multiply x hat by a, 54, and y hat by a. Really, we need to have a column of, we need to have a table of 6 columns, as you can see. For triangle, we would do the similar thing, and for the circle and semicircle, the same thing. The summation of the areas would be 28. You can substitute pi with 3.14 when you do your calculations to calculate the area itself. Then we would sum x hat a and y hat a's. Okay, those would give us basically 3 numbers that we need for our calculations. So the first one is, we have these 3 numbers: area, x hat a and y hat a. As such, we would take the formulas. We simply divide the this number here. This is the summation of really all the x hat a. We simply divide that by the entire area at 28. In this case, that will be the location of the x component of the centroid, and for the y coordinate, it will be 1.42 inches, following a similar format. And the centroid would fall somewhere in this area, with which would be 2.73 inches from this point. This is in the x direction, and in the y direction, it is going to be 1.42. So this distance is going to be 1.42. Of course, this is not to scale the way I draw it, but this is the point of origin. So that would really all into it as far as calculating the centroid for such a composite object. Let's take a look at a concept, a quiz, and see if you can answer these basic questions. Number 1, based on the typical centroid information, what are the minimum number of pieces you will have to consider for determining the centroid of the area shown at the right here? It's like a little cross section here. We basically need the 3 for that, so it's going to be a 3 up here. The second one is could be a little bit more. It seems a little more complicated, but it's actually not. The storage box is tilted up to clean the rug underneath the box. So how do we tilt this? This is the handle that shows here at this point. So we are kind of like pulling this and trying to lift this box. So we are kind of like trying to pretty much lift this box and make it to the position in which we can actually clean what's under it. So we're using that by the handle, and we fix point A is a fixed point. And what we try to determine is what would be the angle, what's the maximum angle of tilt without actually tipping the box over. The correct answer is 60 degrees, and I want you guys to actually go through this problem and let me know if you have any questions on the second concept quiz. It's a good exercise for you guys to go over. Let's take a look at a little more a complicated problem. It's not that complicated, it's just a little more with respect to, in comparison with the previous problem that you have looked at. So we're going to solve this problem, then there's an attention quiz, and I'm going to wrap up our lecture today. So the problem is there are two blocks of different materials. We assemble them as shown. So we call them block A and block B. The densities of the material are different because they're made of two different materials. One could be reinforced concrete, the other one could be steel, could be really anything. But for the sake of our argument, we assume that the rho sub A is 150 pound per cubic feet, and the density of material B, rho sub B, is 400 pound per cubic feet. We would like to determine the center of gravity of the assembly. We would follow the steps for the analysis that I just described to you. So we're going to take a look at each block as a separate piece, and we would follow the same procedure that we did for calculating the composite cross section. So the rho is the volume in cubic feet, and W sub A would be the weight of part A, and W sub B is the weight part B. What we do is we calculate the volume, and knowing what would be the weight per volume or density, right? Then we can actually calculate it. So 150 times 0.5, again, we are calculating the dimensions. For A, let's look at B. The volume would be 6 times 6 times 2, and that's for B. And we multiply that by the density, 400, and this is actually the conversion factor to convert from inches to feet, because remember, we have up here the unit that was given for rho, or for density, it was pound per cubic feet here. So we need to convert the volume that we calculate. It's going to be in cubic inches. We need to convert that to cubic feet. That's why we see that division 12 to the power 3. That's what it really is there here. And we do for A same thing, a similar thing, but for a three-dimensional triangle, as you can see, or like a wedge. It looks like a wedge, but it could be much larger. So we calculated the W for A and B. We set up our table and go over calculating X hat and Y hat and Z hat. This is three-dimensional. So for example, for block A, let's look at block B. It's much easier to show it here. The X direction is here. The X coordinate is to the page. Y is to the right of the page, and Z is to the top of the page. So looking at segment B, X would be what? This is 2 inches, so X would be half of that. So X would be X hat would be 1 inches. Y hat would be 3 inches in this case. It's really actually half of this 6 inch. So that's the Y hat. And then the Z hat, in this case, this is 3. Again, using the same procedure. Z direction is X direction is to the page, and Y direction is here. The second one that I just did was actually for the Y, not for the Z, but they are pretty similar. So in the Z direction, half of 3 inches. In the Y direction, it would be half of this 6 inches. And this is going to be tabulated here. For A, we're using this similar procedure. We calculate X multiplied by A, Y multiplied by A, and ZA, and we show them here: 16.67, 50, and 50. We take the summation of A. In this case, we take the summation of weight. Then we take the summation of XA, YA, and ZA. And we are going to use the same formula we used previously, except we would divide it, instead of A, we would divide it by the summation of W, which is 19.97 in this case, and that way we can calculate the centroid of the location of the centroid of the composite object, X bar, Y bar, and Z bar. And these should be all bars, so this is Z bar, and that is actually a Y bar. Let's take a look at a quiz before we wrap this section up. A rectangular area has semicircular and triangular cuts as shown. For determining the centroid, what is the minimum number of pieces? And then you can use 2, 3, 4, or 5. If you look at this, this is for determining the centroid. What is the minimum number of pieces that we can use? If we divide this, this is a symmetric. It's a symmetric object, and we can really calculate for half of it, and it would be a mirror image of the other one. So all we need to do is we need to calculate for a rectangle, for a triangle, for a rectangle, and for a semicircle, and subtract that from the summation of the other two. So the answer would be 3. For determining the centroid of the area, 2 square segments are considered. Squares A, right here, B, C, D, okay, the big one, and the little one, which is D, E, F, G, right? What are the coordinates, X and Y, of the centroid of a square? We actually subtract, we can, in this case, we can, maybe we should be able, you guys can see this. It's actually 1.5 and 1.5 because it's going to be for this particular square, the bigger one, the A, B, C, D, is going to be right at the center. That's point F. And for this smaller one, it's going to be right at the middle of E, F, G, D. They're squares. It's much easier to calculate them. So it's simply, it's going to be 1.5. Remember that we are, what we're trying to do is we're trying to determine the centroid of the areas. And as such, the correct answer would be 1.5 and 1.5. Okay, and this is 1, and we also use the same procedure that we did as previously. That brings me to the end of this lecture. Let learning continue. If you have any questions, feel free to contact me. Thank you.